Good afternoon, everyone. Thank you for calling back in. My name is Fred LaPolla, and I'm continuing talking about R for sequencing, and in particular, continuing on an introduction to using R and RStudio. So those of you who were here last time on Tuesday, we were talking primarily about the different types of data that R works with, and where we left off was talking about factor data, which is R's jargon for categorical data, be that categorical or ordinal data, which basically is a way of saying data that falls into groups. So things like the sex of the subjects in our study would be an example of a categorical data where we're categorizing in some way. We also, just to review some of the things we talked about character data, which would be sort of like a free text string, numeric data, which is numbers that you can do arithmetic with, and then we've gotten up to factor data. So today we're going to continue our discussion of the different data types, and then we're going to move on to data structures that exist within R and why they may matter to think about with regards to bioinformatics work. And then eventually we are going to move on, if we have time, into discussing what functions are, how you can work with the functions that are built into R, as well as those you may download from packages, as well as if you want, how you would go about writing your own functions. So I was just mentioning that factors are going to mean a type of data where there are different groups. So here we, for example, have we may have pulled in the data when we initially pulled in that NYC package. And actually, while I'm talking about it, I'll go ahead and just provide that R curl, that information, that code for how we would go about pulling that in case anybody has lost that since last time. So just copying that into the chat. But that said, so if we were to look at this data right out of the box, and I'll go back to my sort of blank test information. I may have already classified this, but the out of the box. So I have already changed this one to a factor, but if we wanted to, we could just call it factor. And then what we're saying is by default in this data set, they happen to have coded things 1 and 2. So we can say the levels are 1 and 2. So now if we summarize that, so getting that summary information, we can find out that there's about 642 in group 1, 885 in group 2. So we may not recall right off the bat what that means using the data dictionary, which is just the human readable write out of what the different levels mean. We could recode this to know that this means male, and 1 means male and 2 means female. And so an option that R provides us with is that we can actually go in and recode things. So passing it a list of terms. So here we have 2 terms for 2 numbers. Passing that into this command levels NYC $gender. Something really important to note is the order of this needs to follow the order of our levels. So if we had written female, comma, male, then level 1 would be female and level 2 would be male. So it's really important that when you are renaming your levels in R, that you follow the exact order that goes with the numbers here. So this is just 2 of them, relatively simple to keep straight. But we can imagine, let's say we had something that was 4 levels and we had different terms for them. We would want to be really careful to make sure that the order that we added the labels in was the exact same as the order of the numbers that corresponded to those labels. But this can make it easier to view this. And eventually we're going to get to a point where we're doing data visualization and building charts. And then it can be really nice to have this written out as male and female versus just 1 and 2. You could also, if you prefer, give both the labels and the levels at once. So you can say factor, for example, in this case, age group. And so we can say that there are 3 levels because they have coded them 1, 2, and 3. We could, if we wanted to be specific, give the actual age ranges that are from this data set. for today's purposes, it doesn't really matter too much. So I've just called them youth, middle, and aged. And then we get this summary. Some things that are really important to note about factors, and in particularly assigning these labels to them. One is, once you've done this once, you're not going to want to keep running this command, because what this is saying is go into this age group column. When you see a 1, call it youth. When you see a 2, call it middle. And when you see a 3, call it aged. But once you've run that once, it has recoded those values as youth, middle, and aged. So if you try to run it again, it's just going to change everything to an NA, because there's no more 1s, 2s, or 3s, and you'll need to reload your data back in. So it's really beneficial when you're doing this to really only run it once and check if it's worked. If you keep trying to rerun it, you're going to change the data and possibly overwrite it and have to pull in your CSV file again. Something else to note about this, for those of you who maybe have had experience in other statistical tools like SPSS, for example, the levels and labels here are a little bit different. It does not sort of encode these labels as a separate value from the what here is written levels. What this is just doing is it's going in and looking at this column and seeing that there are these 3 groupings, in this case 1, 2, and 3, and assigning them these text values. So this may be a little bit different for those who have worked with other tools. And it's important to note that then from here on, once we've assigned these labels to this value, when we want to perform some analysis, so let's say we just want to see what is the proportion that fall within the youth group, we need to type in youth. We don't want to type in 1, 2, or 3. So it may just be sort of a different way of thinking of things that is sort of a quirk of working with R. If you've not worked with other programs, don't worry about that too much, but just be aware that once we've recoded, we're going to want to refer to youth, middle, and age, so the text value we've assigned, not just the 1, 2, and 3 that it used to break up the data in that column. One other thing I did not mention at the beginning of today's class, but I have at the beginning of others, if you run into questions as we're going, I encourage you to use the group chat, and one of our TAs should be able to jump in and respond. Another type of data that exists within R is what's called a logical value. And so R understands, if we type in the words true and false without quotation marks, this is meaningful to R. So here we can see last time it's sort of writing for, and it understands for, but for in quotes it does not. If I write true, we'll note that it also gives this blue text in contrast to some other words, such as my name, or not my name, the word fish. It doesn't understand fish, but it understands true and false, which are in blue, because these are the logical terms. So some things to note, that when we are interested in if something is true or false, it's also equivalent as though true was a 1 and false was a 0. So this can actually be really useful to us. So just to show a little bit of what I'm talking about, by default, if we said, if we put in a logical command, so using one of these logical operators on this page, I've used the less than. So if we say, and I'll show more of those in just a moment, but if we said NYC SPH less than 50 and run that, it's going through that column. And this is a lot to look at, so we wouldn't normally do this just for analysis purposes, and it cuts off, I think, at 1,000 rows. But if that row rather, is under 50, it tells us it's true. And if it's over 50, it tells us it's false. In this case, because there's so many, this is not too useful right off the bat. But knowing that the true corresponds with a 1 and a 0 corresponds with a false means that we can actually use this to find out descriptive statistics about our column of data. So one option is running the mean command that we've seen sort of as an example on the same logical statement. So we want to say, what is the mean of when it's true versus when it's true? So basically it's taking the sum of all of those trues and then dividing them by the full length, which is a way of getting the proportion. So here we can see just under 2/3 of people in our NYC Haynes study are under the age of 50. And this is a relatively quick way we could find this out. We could also see, for example, if we did sum instead of mean, we would be quickly getting the total number of people under 50. And that's because of these logical values that are coding as 1 and 0. So we've talked about a lot of the different common types of data that you may be working with in R. And it's often very important to figure out what we're working with, especially because, as we've seen already, when we pull in a table of data, a spreadsheet of data, often R is going to code it in some way that we don't really want it to be. It's making its best guess, but it doesn't have to be what's the word? Correct. It's not always correct because it is sort of a guess. If you're getting an unexpected message, it may be that there's a spacing error for those providing messages. So in this case, if I run class, I can find out exactly how it is treating that data. When we initially ran it in, we can run this on a column. We can run it on individual cells using the indexing, and we can also run it on an entire data object. So we could run it on all of NYC to see what is the structure of that. So class is a very nice way to explore your data and see what the structure is. And that will be useful to you so that you know that it's classified things correctly, first of all. And second of all, that you can do the types of analysis that you intend to. If it's classifying a numeric column as character, for example, if there was a typo or a stray letter in a column, you may want to coerce that back to numbers or go and find that, that typo and correct that. And so you can know that through class. So then you can run numerical analyses. Similarly, for example, finding things like proportions of groups, you're going to need it to be in a factor. So class is really going to help you out to get a sense of your data. So we've talked about a few different data types, and by data types, I'm really saying what is the type of, or what is the general characteristic of a given cell, for example, or a given column of my data object. But there's also, on top of that, several data structures. So the data itself is contained in, essentially in what we can think of as the equivalent of cells, but then there are different structures organizing that data. So I'm actually going to go, so there's a few ways we could talk about this. We could talk about things from most simple to most complex. I actually personally like to think of things from most complex to most simple. And the reason for that is my background. I've always sort of, as a default, started out thinking in terms of data, in terms of things like Excel spreadsheets, as sort of a normal way to store and organize data. So the first and most complex type of data, structure of data, I should say, is a data frame. And a data frame you can think of as essentially a spreadsheet. So you have columns and you have rows. Each of those columns typically is going to have the same type of data. So you're going to have column 1, you might have, for example, age. Column 2, you might have gender, and so on going through. Those don't exactly correspond to our NYC columns. But different types of data. So you might have factor data in one, you might have numerical data, text data, and so on in the different columns. And each row in this case is going to be a different record within our data frame. So this is just saying the same basic things. So any given row, if you read it across, is going to have different types of data. So if we just sort of look at the first couple rows of NYC, we can see we have any given row has essentially text, categorical, numerical, categorical, categorical, numerical, and so on. I think that's kind of the extent of this specific data frame. So the next slightly more simple form of data is, or structure of data is a matrix. And a matrix will be very important to those of you working in RNA sequencing and gene expression data, because a matrix will be the data structure that you often need to get your data into to run your analyses, to run the analyses that will go with RNA-seq and gene expression analysis. So a matrix is like a data frame. You can think of it as still having that tabular columns and rows. Tabular in this case is just referring to those columns and rows format. But the important difference between a matrix and a data frame is that every cell in a matrix is of the same type as the other cells in the matrix. So as we will eventually learn about, there are certain commands that either automatically convert a set of data into a matrix to run its analysis, or you may have to yourself manually convert your table of data into a matrix. And because the matrix wants every column and row to be the same type of data, so by same type, I mean character, numeric, factor, and so on, you have to really be careful that since typically you're going to want a matrix of numeric data, that in that data frame, you have no text or no values that are going to throw that off. I really want to belabor that point because it can be a sticking point and confusing, especially as you're starting out working, but especially when you're trying to, for example, make a heat map. It's going to be really essential that all of the data in your matrix is numeric and that you have formatted it correctly. And it's also really helpful to be aware that because things like a character string are there's less rules, like you can have numbers, you can have letters together and they're still characters. It's often the case that when we convert things to matrices, if we do have those spare letters or we do accidentally include a column that maybe we shouldn't have, it's going to treat everything as characters because it wants everything to be the same. So hopefully the main takeaway is just going to be that the matrices are columns and rows, but everything is the same type. And so for numeric-based analysis, like gene expression, like RNA-seq, we're going to want to make sure that everything is a number and there's no spare letters and we don't pull in columns, for example, of names into our matrix. We can talk about how we'll be able to assign names to our matrix rows, for example, or matrix columns, but we don't want that to be part of the actual matrix of analysis. So the next type of data that we'll be talking about is a list. You could think of a list as essentially like a row of a spreadsheet. So you could have different types of data in a list. In my experience, it's not really often the case that you'll work with lists all that much, which is kind of why I've moved it down. But it may be the case that for your specific types of data analysis, you may be working with lists. But the main thing is you can think of them as groups of objects, sort of unidimensional. So instead of having both multiple columns and multiple rows, you can think of it as one row with multiple columns. And then the last item within the data structures is called a vector. So a vector is, again, similar to a list, so it's unidimensional, but it's only going to have one type of data. So again, it's a little bit more like the matrix of lists. So it's all going to be one type of data, and you can just use that same C, that concatenate, to sort of group for, in this case, numbers together and create a vector. So some things to note about vectors, especially numeric vectors, is you can perform mathematical operations with them. You can, for example, multiply them. And when you do this, if they're not of even length, it will do what is called recycling. So here, if we want to see, we've created a small vector, just 1 through 4, another small vector, 2 and 3. And if we multiply them, we see the results we get are 2 times 1 is 2, 3 times 2 is 6, and then it recycles back because this one's half as long as this one. 2 times 3, 6, 3 times 4 is 12. So if you are doing work combining vectors in this way, it can be really good to note that this is going on and that it's sort of cycling through the through sort of the position. So we could think of this as position 1, position 2, position 3, but in this case, because it's only 2, this one recycles and would continue to do so if they were of greater length going through. You can also combine vectors into a matrix. So there's 2 commands that would really commonly be used for that. One is called rbind and the other is cbind. And so rbind stands for row bind. So here we can see X, so 1, 2, 3, 4. And here it's done the same thing. It's gone 2, 3, 2, 3. If you have uneven lengths, you're not going to be able to do this. So down here, I've just made a note that we've, for example, if we have a new vector, which we're calling Z, so I've just given it some random numbers, 5, 8, 0, 9, 10. The important thing to note here, the length of Z is 5. If we try to combine these together, it's going to give us a warning. So I've just sort of done this down here. They're not a multiple of one another. Oh, but it is still allowing us to eventually, let's see, to cycle through, to recycle going on. So it's good just to be aware that if they're not multiples, it will give you a warning that something is sort of amiss. So rbind is combining them this way. Cbind would be if we wanted to add columns on to the side. So that's the main difference between those two. We could also, if we wanted to, so I mentioned names earlier, we could apply names to these objects, to these cells essentially within our vector. So here I've just given them the names 1st, 2nd, 3rd, 4th, and I've used this command names of X. So if you remember names, or X rather, was just the numbers 1 through 4. And now because there's these 4 spaces within our vector, we've given it these 4 terms and they're applied there. So this is actually something that can be useful if we want to apply names to, say, a matrix. So we could imagine, let's say we do have a series of genes. We're looking at the expression at different time points. We would want the names of those genes to be a name. We don't really, that's not really the data that's going to be, for example, combined into the heat map. We don't want the labels of the individual genes to be colored in a heat map. So we would want to be careful to sort of keep that separate at first while we're making just the matrix of the actual gene expression data. But then we could take a list of those names and feed it into the names command. So the names of our, for example, our gene expression data, and use those as labels that sort of, if you imagine, they'd appear off to the left of our actual data. And that can be a nice way that we can still have meaningful data, but it's not trying to treat those gene names as data that sort of needs to be analyzed. So similar to the data structures, or the data types, we can find out the data structure by looking at an entire data object. So if we run class of NYC, it tells us it's a data frame. And typically when we read in a CSV file, so those spreadsheets, it's going to treat that as a data frame. And so we may need to reclassify things. I'm going to sort of skip over that. So here we could see if we looked at various different types of data, we can find out if something is numeric, and so on going forward. You can even do it for an individual cell down here. So we've done class of NYC row 4, column 5, to see that that is an integer. So I mentioned that often R will read things in the wrong way. And it can be really beneficial to us to be able to reassign the data type. So we looked a little bit when we were talking about factors, about reassigning those factors. So we might want those groups 1 through 3 to be either young, middle, or oldest, or something that's going to make sense. We could give the actual information as well. Something I'll note is that there are also these coercing commands. So there'll be as factor and as matrix for coercing a column. And so it may not always be completely apparent. And it's something that, to be totally honest, I would recommend examining that the end result is providing you with the type of data that you want when you're using these. So it's trying to convert it in some way to either a factor, but it may be worth trying out to see if it's giving you the end results that you're expecting. So just something to keep in mind. So I'll hold off on that. So we may want to create a matrix. So if we go back and look at the 5th through 10th and 6th through 9th rows, or I've just chosen a few rows, but the columns 6 through 9 are all numeric. Do it over here just for the sake of argument. So we do columns 6 through 9. We can see these are all numeric values. And I might even say, let's say, what are the class? Or I might just say data frame. So I might have to, there are ways I could look at those individually, as well as using things like apply. But in this case, let's say I wanted to make a matrix out of that. Later on, when we're doing more with data visualization, we'll pull in some gene-related data to try out converting that to a matrix. But for right now, let's just try turning this to a matrix. So what I might do is I could say, we could give it any name. We've given it sort of a jokey name there, but we'll just say want matrix. And so I'll just give it the first couple sections. What did I do in the example on the slide? 5 through 10 and 6 through 9. And again, I've chosen these columns so that they remain numeric. The rows really don't matter too much. Those should also be numeric. And again, if we test what is that object, we see it's still a data frame. So we want to try to change that to a matrix. And so I'm just going to try out this as matrix. So we can tell it how many rows and how many columns. So looking back, we can see 5 through 10, 5, 6, 7, 8, 9, 10 is 6. And similarly for the columns, it's 4. And so we can just say, and I'm going to feed it back onto itself to basically overwrite itself as a matrix. So want matrix as dot matrix, want matrix and row, to n row or n rows. Got it conveniently written. Oh, it even's popping up, so and call equals 4. And now if we look at the same thing, it should just look basically the same, but all be numbers. And if we do class, it is telling us it's a matrix. So again, it may look very similar from when it was a data frame to when it was a matrix, but from ours understanding, everything in this matrix is going to be the same type of data. So all of these are going to be the same as all of these, so all numeric. These labels here are just labels at the top. They're not really part of the data that would be analyzed. They're just kind of there to be more human readable. And this, again, it will be helpful when we want to look at things like the heat maps, for example. We can also, as well as doing math on, if we're doing matrix math, we could also look at an individual cell just to see what type of data it is, because sometimes it will pull things in and we think we're fine, but maybe we didn't realize that one of our columns was a factor. So maybe we left it as 1, 2, and 3, but it was a factor. Because the factor kind of has more rules than the numeric, it may treat our whole matrix as a table of factors. So there's a question in the chat about when might we use a data frame versus a matrix. I would say that's really going to depend on the type of analysis that you're looking to do. So as you progress in this class and do more of the sequence analysis, you may need to use matrices for that. If you were just doing if you were storing different types of data and doing kind of what I might tend to think of as like plain vanilla type stats, you would not need to convert it to a matrix. A matrix has kind of more rules to it because every column and row has to be that same type of data. Let's see, code not able to find as matrix. So R is case sensitive, and that's a very important thing that will always come up. So you do just want to remember the lowercase. And I will say definitely 9 times out of 10, I mean, I hit that error relentlessly, you know, either some accidentally capitalized letter or some small flip of, you know, of letters. There's no shortage of times making these materials. So these materials were produced in R, where I had accidentally typed NCY and then get the error. So it can be frustrating for new learners to R, but it's definitely something to be aware of. Oops. So these are things that you can try out on your own at home, on your own time. I'm going to sort of switch gears. We've now talked about different data types and different data structures. I'm going to sort of move over to talking about different functions and what are functions and what does that mean with regards to R. And so far we've basically, to sort of review everything we've talked about pulling data into R and into RStudio so we can do something with it. And then we've talked about what sorts of things might we be working with. So what types of data appear in what are often columns and spreadsheets, or columns and rows rather, and then what are the different structures that exist. So moving forward, I'm going to talk about how we actually do things to and with that data so that we can get it to a point of analysis. I also see some comments, and I will add a third to that I also almost exclusively work in data frames. So I do, in my life, I very seldom, if never, am working with matrices for my own data work. But again, for you, that may be different because there are cases where you do need the matrix. Oops. So today we're going to talk, so in the last, I guess, half hour of today, and definitely going into next week, we're going to talk about functions. So just some review questions for you to think about. So I'll actually just give away these answers rather than have you answer them. So the data structure, most like the spreadsheet, since there are these questions here, is going to be that data frame. So different types of data in columns of your data, different columns. The matrix is all going to be the same. And you can look things up with that class command. So class parentheses, and then the either data, whatever data object you're interested in. So if you do not have the data in, whoops, I'm going to copy and paste all of this for you. And actually here, I've gone ahead and given labels to our categorical data and given it names. So we've got age, gender, HSQ1, which to be honest, I don't recall off the top of my head what that specifically means. And then DX, DBTS, which in this case, there were 3 levels of diabetes, what's the word? Diagnosis. I'm not really sure how they have diabetes without diagnosis or what that necessarily meant. So that will have to be a mystery. If you really are interested, you could read more about it online, but for today, it doesn't really matter. Okay. So far we've worked with some basic kind of out of the box functions. So I've been using mean a lot because at least for me, it's a pretty straightforward operation. So if we can say mean, and then in this case, 1 through 10, we could also try mean and a column of our NYC data frame. And we might get information, we might have to tell it to remove some NAs, but basically the commands that we're giving to R, so class, so on. A very helpful feature of RStudio to remind you of, when you encounter a new function or a new command, I really recommend checking it out with this question mark. It can be a great way to learn about it. So there I've done mean. It's not going to be the most interesting. If we just do it here, it's going to tell us over here in this help box that it gives us the arithmetic mean. Let's see. And that it expects some X trim. If they're trimming things off, we can go down and learn about it. May or may not be necessary for you. NA.RM is going to be very commonly used, and it's saying, will this remove any NA values? So often, if we're getting NA as the result of something like mean or some other operation, we may need to remove NAs from our data objects. So we might want to use that na.rm command. So it can be a little bit difficult to know which arguments are required right off the bat. In this case, trim, it may not be apparent if we need to use it or not. And to be totally honest with you, it's going to be a little bit of trial and error, as well as seeing what others are doing online. So when we go to sites like Stack Overflow, when we see descriptions of commands on our bloggers and other websites, often we'll note that they're not giving us every command. So another one that, to go back to one we used in the first session of this class, we do read.csv question mark. That's part of a family called read.table. If I go down, there's a whole great deal of commands, and they even sort of trail off with an ellipse. But as you're going through and on your R learning experience, often you'll see that people are pretty much just giving a file and maybe if there's a header or not. And so it can just be good to keep an eye towards that and be aware not every command is, or every, what's the word? Not every object or argument is going to be used in every cases. So you can actually write your own functions. And I'll say I actually personally almost never do this, but mentioning it sort of a fundamental part of any sort of coding instructions. And it very well may be the case that you and your research lives are doing this. But for me, who I tend to do kind of very plain vanilla descriptive statistics for creating reports, it's not typically super necessary to do something beyond what sort of comes out of the box or comes out of a lot of the packages. And those packages we talked about, somebody has actually created those and written those functions that come with that. So those people have really taken the time. So if you do get to a point where you decide you're not seeing a package that meets your needs, you may want to create your own functions. So the first thing to note about functions is you would give them a name, just like the other objects. So just like the data frames we were talking about, just like those vectors we were talking about, you're going to want to give your function some sort of name. And the general format is always going to be, so you're going to actually write out a function of, and then however many values you have. So here I'm saying a function of n, so of one number, so one variable. And in this case, unlike when we were naming, say, a vector x and y and z on the previous page, n really is a variable in that kind of mathematical sense. And then we have these curly braces where we say, take the mean, so we're actually using a different function in that, of n, some n that's going to be provided, and multiply it by 2. So in this case, if we assign n to be 1 through 10, we can do double mean function or double mean func of n. So the mean, as we recall here, because we'd assigned it to be this value, was 5.5, but times 2 is 11. So again, the main thing to note is that you'll have the phrase function, some amount of variables, and then in these curly braces, the actual function that you're telling it to do. So sometimes we are going to want to do, or maybe even often, we're going to want to kind of do the same thing across many either rows or columns of our data. So we may be interested in this case, I'm just doing something like mean, but perhaps we're interested in something more useful, like we want to know if there's correlations between different columns. And we could technically write these out one at a time. So mean 6, mean 7, mean 8. This may be time consuming and it may be kind of messy, especially if you're dealing with a lot of data. So 3, that we see on the screen, not really a big deal, but you may want to go through more than 3 columns. And so there's a few different ways we can do this to do kind of what I'm going to call repeating these functions, some of which are kind of specific or I'm not sure if they're exclusive to R, but they're definitely used primarily in R. Others you may recognize from other coding languages for those who have done other coding. So I decided to start by talking about something called apply. And we can also talk, and we will also talk about something called for loops for those of you who've done coding in other contexts. I decided to talk about apply first, mostly because various R experts have written that this is more efficient than using something like a for loop. And so it's kind of the preferred community best practice for working with R. And I'll definitely admit I'm not a computer scientist and I work with very small data. So it does not really tend to matter too much if I'm working, if I'm using how essentially efficient or how efficient my code is. But in your life, especially those of you who may be working with big data, who might be going on to work on Big Purple, it may actually matter a great deal more than for me. So the first thing I'm going to talk about is this command apply. And apply is basically it's actually a family of commands that allow you to do data across, I've written slices of matrices, so you could do it across columns or rows. And the general format is going to be the data frame where you want to run the function. And it doesn't actually have to be, for example, the whole NYC data frame. We could specify NYC and then in the brackets, columns 6 through 9, for example. So we only have numeric data. Then we can tell it if we want this function to be run over rows or columns. So we could say, do we want, in the case of mean, do we want the mean of the, I forget exactly which values 6 through 9 were, but do we want the mean cholesterol, mean blood sugar level, mean so on? Or do we want the mean for each row, the mean of each individual going down, assuming that those different columns were related in a way that made sense for doing that? And then finally, the function. So to actually illustrate what this looks like, it will look more like this. So X, the data object, margin, that just means that this, and for apply, it's going to have one of 2 values, 1 or 2. 1, I believe, is rows, and 2 is columns. Always a good thing to double check, though. And then fun is just going to be the function. So in this case, it would have been mean. So an actual written out example, first we specify the data frame of interest. So we've got NYC, comma, 6 through 9. 2 is columns. So for this data, it's not going to make sense to take a mean across rows. It wouldn't really be meaningful to sum up the, in this case, I forget where it started, but it wouldn't make any sense to sum up, for example, the glucose levels and the mercury levels and the cholesterol levels and find the mean of that. That's a meaningless number, whatever that happens to be for any individual. Conversely, it might be interesting to us to look at a column to find out what is the mean mercury level of our population, what is the average cholesterol of our population. Going forward, probably on Tuesday, we'll talk about how we could then break down and get subsets of our data. So we could say, for example, what is the average cholesterol of diabetics versus not, and so on. But for right now, the main thing is that we could get these, run these functions across a bunch of different columns at once, so we don't have to spend as much time typing in the code. Oh, and then the last thing, actually, which I'll note, So I've talked a few times about how with mean, we might want that na.rm, and often for these arithmetic sort of commands, we're going to want to remove NAs. So here I've just sort of added the commands or the arguments that go with mean over here to its right. So it's after a comma. And I mean, I definitely would not expect you to memorize all this. So again, this would be a great time to remember the question mark apply. Let's see, it's being slow. There it goes. And it tells you basically the same information. So yeah, 1 or 2 for this information. And going down, the other nice thing about these question marks, if we go all the way down, you actually can see written out examples of code. So here it's got this matrix, and it's saying to get the sums, for example, or it's naming this to be the column sum. So that's already a command that exists anyways, but if you wanted to, you could do that there. The other thing actually that's really important to note is apply automatically converts our data frame, whatever subset here, into a matrix. So it is important to note that we want these all to be the same type of data. Some of the other apply commands might not do that, and so it's just a beneficial thing to be aware of. So an example of that would be, I guess I sort of jumped ahead in my slides, but an example of that would be, let's say we've run the class across the first 3 columns. The first column of our data is the key. And so even though age is a number, because key is a character, it's just going to treat everything as characters. So it may make life difficult. If we say had to assign that to be some other object that we could refer to, now it's going to treat this as a matrix of characters, and it's going to be kind of hard to do any sort of interesting work on that because it's not understanding that those are potentially numbers, because it wants it to be a matrix where every value is the same. So going down, let's say we did this over here and it treated these like characters. If we then tried to get the mean of that, it's saying NA for all of them, because it's trying to get the mean of text, which doesn't have any meaning in R or in anything really. So the main sort of takeaway is just to be careful when you're working with a function like apply, because again, it's going to convert the data you've passed to it. And by passed, I mean put into it. There's also a command sapply. It's a relatively simple option just to be aware of. So you don't have to specify, it'll just do these columns here, which may be nice. There's a lot of these different types of apply functions that you may encounter for different purposes. So there's one mapply, vapply. I don't really remember all of them. I'm mostly mentioning just if you do see them to be aware that they are of this apply family, where they're going to be passing some command over rows, sort of cycling through, and that you can always look up exactly what those are doing so as to be able to make those changes. So I've talked about apply, and in general, a lot of people who tend to talk about what they're doing in R tend to favor apply for whatever reason. A more universally used option might be what's called a for loop. So those of you who have done work in coding in some other environment may be familiar with a for loop. And it does allow us to do a very similar sort of moving through rows or columns of data, similar to that apply function. So the for loop is going to basically say, for some values in some set of numbers. So earlier we were talking about columns 6 through 9. So for a number between 6 and 9, so like, for example, the number n, for n in 6 through 9, do something. So in that case, it would have been mean of each of those columns, mean of NYC square brackets, comma, n. And it will cycle through. Oops. And so an actually written out example might be for I. I is just a value that's often used as this sort of example for loop variable. for I in 1 through 10. So it's going to start at 1 and then go up until 10 in integers. Do I times 3 and assign that to be I and print I. So here we can see it starts out at 1. So 1 times 3 is 3. Call it 3, print 3, or print I, which is 3. And then 2 up here, 2 times 3 is 6, so printing 6. 3 times 3, and so on. So a way of counting up. That print is just so that we have some output. Something that you might note is there's this 1 in square brackets. What that's sort of signaling to us is that's the first output of each iteration. So each time it's pretty much writing over the previous iteration of our loop until it gets to 30. So perhaps what we want to do is we want to do essentially what we've done before using apply to sort of go across the columns to get those values, to get the means. So here we're going to say for I in 6 through 9. So I is that value and 6 through 9 is the range of numbers that I will be before it stops. We're going to say get the mean of the ith column, so the 6th, 7th, 8th, 9th column. Also remove any NAs so we actually get a result. And let's just call that value. And then print out both the column names of NYC of that column, of that ith column, as well as this value up here. So what it's doing is it's saying, at first it starts at 6. So it says, give us the mean of the 6th column, which happens to be U-creatinine. It's assigning it to this value, and then it's printing out the name of that column and its mean. Then it's adding 1 to it because it hits the end of the loop, and now it has to cycle back. So it was at 6, and now it's at 7. And so it does it for the 7th column, so on with the 8th, goes through, so on with the 9th. So these are not actually stored in any sort of table. It can be helpful to note, like we could read and look up what that information is in the output. But basically, if we were to look at this information it's not stored anywhere besides on our screen. So we couldn't really use it for further analysis as it currently is. You do have the option where you can use this for example, creating new variables. So I've done it just for the first 100, just to lessen the runtime. But let's say I wanted to get the cholesterol ratio, which is the total divided by the HDL. I could say, go through for the first 100 rows in this case, assign in the ith row, so 1 through 100 rows, this new column, which has previously not existed. And we can say, go here and divide this row's cholesterol total by the same row's HDL. So the first time it will be person number 1's total cholesterol by their HDL cholesterol, and it's going to assign it to this new 24th column, as it were, the col ratio column. And then it's going to cycle through 100 times in this case. So it could be more. Typically, you'll get the wheel spinning a little bit at this point. And then in this case, I said, just give us a histogram of this so we can see, what it has given us out. Let's see. So the question is, if you want, there's a question in the chat, if you want a loop to occur in columns 6, 7, 9, but not 8, could you do the C? That's a good question, actually. I would have to experiment with that if you're allowed to do non-sequential loops. So that's a great question. It might also make sense to sort of create a subset. We'll talk about a couple ways you could do that going forward, probably on Tuesday. But that's something I would want to experiment with to see what the most sort of efficient option would be. So you may decide, there are times when you might want to use for and when you want to use apply. One is you may want to have full control of what is done in each level of the calculation, as well as if you have data with a complex nested structure. So jumping forward, so there is this concept in R that we've sort of looked at called vectorization. Basically, the long and the short of this is, because R out of the box has this sort of 1 through 10 functionality, we're not going to want to program in for loops that could be done more simply than by just sort of the built-in functionality. So if we had a vector, so thinking back to the previous slides of sort of the earlier section, so if we had a vector, which is just, in this case, the numbers 1 through 10, if we multiply that vector by 3, it essentially is going to do a for loop, but it's going to be a little bit faster. It's going to be easier for us to write without having to write this out. So I times 3, when I is the numbers 1 through 10, is the same as what we have here in terms of the results, but is a lot quicker and uses up less of our, it's more efficient to do it this way. So the real take home is, if you're able to do these sort of vector commands, I would recommend doing that over writing a for loop. Another recommendation, I'll show it in a moment as probably the last thing of the day before we move on to if-else statements, is you can, and sometimes people will do, but the general recommendation that I've seen in writing is to avoid adding things like cbind within the loop. And the better option is to do things like to set up a blank vector or matrix at the beginning of your analysis of before you actually start the for loop, and then sort of have that populate the blank object rather than sort of binding things one after the other. Basically, my understanding is it sort of slows things down to do that. So an example, let's see, is it on this one? So yeah, here down at the bottom, I mean, you can just create these blank, this is just showing you can create blank vectors. So mode numeric, meaning it's a numeric continuous stretch of numbers. It's 99 long. So then if you print it, it just tells you it's all zeros. Similarly, the matrix, this is the same as writing 0:12, but and doing four rows. So just going across that way. But to actually show it, so you could give this blank vector, I call it test vec. It's numeric, it's 3 long for the 6th through 8th columns. And then there probably actually is a more elegant way. I just did I minus 5, so it'd be 6 minus 5, so it'd be in the 1st, 2nd, and 3rd of test vec. Otherwise, it will still appear in the 6th through 8th. Take the standard deviation of the ith column, the 6th, 7th, and 8th columns, and just remove that NA and assign that into this blank vector. And then this ceases to be blank. And then this last sort of step before we print it is just to give those names of the NYC columns to the test vector. I realize I went over that kind of quickly, but we will be discussing, as we go forward into next week, we'll talk a bit about if-else statements, as well as subsetting and doing data cleaning to get us ready for more data analysis, and eventually moving on to data visualization. So rather than jump into a new topic with 2 minutes remaining, I'm going to sort of end there, though I can hang out a little bit and see if there are any questions in the email, or in the chat rather. Also, as Lisa Beth has posted, there's the link to the class website, which is where we will also have links to the materials. Also, actually, one thing I will note before we sign out, to make life easier for our TAs, please refrain from writing thank you in the chat, because it radically causes the scroll speed to go crazy. And if they're trying to read a question, it's very hard for them. So while we appreciate the sentiment, when you're done, feel free to just sign out. No need to write thank you, because it does sort of create a little bit of chaos in the chat box. So thank you for your time, and I'll see you all on Tuesday.